Hello students, welcome to Apna Tutor channel. In today's class, we'll study another topic of electrostatics, that is Gauss law. In the previous lecture, we have seen this image which depicts the electric flux that is passing through the surface. So we have seen that electric flux is the number of field lines which are crossing through the surface. And it depends on the electric field and the area vector. So we have seen the area is a vector quantity and its direction is outward normal to the surface. Okay, and it also depends on the theta angle, and theta is the angle between electric field and area vector. Now let's recall the flux where we have seen that when the surface is perpendicular to the field, so when the field lines are in this direction and the surface is being perpendicular to the field, now the angle between area vector and electric field lines is this theta is equal to 0 degree. So we get a finite value of flux. So and now as we go on increasing the angle, so we tilt the surface through some angle theta equal to 30 degree, and now the normal vector changes accordingly, but electric field directions are same. Therefore we say that the angle between area vector and electric field comes to be 30 degree, and we get some another value of flux. So we see that as the theta goes on increasing, our flux goes on decreasing, where when surface becomes parallel to the field. So let's see it from the here. When the surface is something like this, and the area vector will be in this direction outward normal, and the field lines are still going horizontally. Now we see that the angle between field lines and the area vector is 90 degree. So now the surface is parallel to the field, and here the diagram will not be appropriately clear to you, so I have drawn over there and explained you. Okay, now we see that the flux becomes 0. Now none of the field lines will cross the surface. All the field lines are moving along the surface. Okay, so as I told you in previous class, you can imagine it with the flux of water. Take a circular ring or any shaped ring surface. So you can try it at home, and you can see by taking the water flow, you will come to know the flux variation. Okay, so this we have seen in the last class, and now we'll move on to today's lecture. So what is Gauss law? Gauss law. So Gauss was the scientist who gave the law that whenever the flux is passing through the closed surface, so we have a closed surface, suppose we have a closed body, okay, and we have to find the electric flux through the surface, and suppose we have a charge over here. Now we have to calculate the flux through the surface. So instead of applying this integral E dot dA which we have seen for the continuous objects, okay, so instead of applying over the closed surface, the symbol is for the closed surface, so it is specifically for the closed surfaces. Instead of doing the calculation of the integral, we can directly say that the flux, electric flux through the closed surface will be 1 by epsilon naught times the charge enclosed by the surface. So this is the charge enclosed, the amount of charge enclosed by epsilon naught. So we can directly write it like this. Okay. Now according to the Gauss law, total electric flux passing through the closed surface, so it is an important point, electric flux passing through the closed surface is 1 by epsilon naught times total charge enclosed. So another important word, enclosed by the surface. So you must include these both words in your definition, that the Gauss law states this. Okay, now suppose if I have some closed surface and I have charges q1, q2, q3 over here, q4 over here, and Q5 over here, right? So I am saying that flux will be charge enclosed. So the charge enclosed will be Q1 plus Q2 plus Q4 by epsilon naught. Okay, so there will be no contribution of charge 3 and 5 in flux. Okay, now there are some points which are needed to be kept in mind. So you can note it down that for the Gauss law, we must have the symmetrical charge distribution, and it will be only applied for the fields obeying inverse square field. Okay, sorry, it would be inverse square law. So we have seen this inverse square law field in our class 11th also, that is the gravitational field. So we can also apply Gauss law in that case, right? Now some another important points are flux through the Gaussian surface is independent of the shape and size. It is independent of shape and size. Okay, suppose I have a surface like this of radius r, and again I have another surface that is of 2r. Okay, and we have a charge over here. So the field lines will be all the way this way. Now the flux through the r and 2r will be independent of shape and size. Now I should tell you what is the Gaussian surface. It is a hypothetical surface which we draw over the closed surface, and we must keep in mind that flux through the Gaussian surface is only due to the charge enclosed by it. So it is important point that flux through the Gaussian surface is only due to the inside charges, while the electric field at any point of the Gaussian surface is due to all the charges whether inside or outside it. Okay, so as we have seen in above example that flux is only due to the Q1, Q2, Q4 charges, while the electric field will be due to all the charges present over here, right? Moving on to the further, we see that Gaussian surface depends on the symmetry. Now how we have to draw this hypothetical Gaussian surface? It depends upon the symmetry. Suppose we have a point charge. So for the point charge, we'll make a spherical Gaussian surface. We'll see in later examples that for the point charge we'll draw spherical Gaussian surface, right? I'll write it this way, G surface. And for the either for the wire or we can say for the cylinder, we'll be drawing the cylindrical G surface. G surface means the Gaussian surface, right? So as we are now having the idea of the Gauss law and the Gaussian surface, now we'll see the applications of the Gauss law. Okay, for the applications we will have some derivation part. So in order to understand that, we must first see the Gauss law in our real life. So where the Gauss law is actually applicable. So we have seen that electrostatic shielding, it is very important phenomena which is also known as the Faraday cage. So how does Gauss law is applied over here? It explains that why the electric field lines are not present over inside the conductor. So we must have heard these examples that during the lightning, if you are traveling by the car, it is recommended to stay in the car, and that car also behaves as the Faraday cage for you since it is metallic in nature. Since now we know that electric field will be zero inside it and it will be protecting us from the lightning. So here we'll see how Gauss law is valid. We'll derive it with Gauss law. Okay, so the next example is charge on the conductor. So we have a conductor, and we see that the excess charge on the conductor is residing on its surface only. So we have seen in the Van de Graaff generator, as well as the derivation part will also help understand it, how the charge resides on the surface. Okay, and then we have capacitors. So the capacitors, the electric field lines inside the capacitor, we'll see that it is equal to sigma upon epsilon naught, and this can also be explained by the Gauss law. Further, we have electrostatic precipitators, which are used to remove the dust and the smoke particles from the industrial emissions. So it helps in air pollution control. Then we have the lightning rods, where we see that if we have the sharp edges, so at the sharp edges, or the sharp points, we say that strong electric fields are created, and they ionize the air, and the whole of the lightning directly moves to the ground. So it is also one of the protecting systems. And then we have the semiconductor devices. So it is one of the powerful law which is used in our real life. Okay, now let's understand it through the derivation. For the derivation part, let's start simply with the electric field due to the point charge. So for the applications, electric field due to the point charge. Now, as I have told you that we have a point charge, and for the point charge we will be drawing the hypothetical surface, that is spherical Gaussian surface. So I'll draw it over here, my spherical Gaussian surface. Now for the point charge, electric field lines are radially outward. So we'll draw it in this way in all the directions. So electric field lines will be radially outwards. And we have the Gaussian surface sphere of radius r. Let us say that the sphere has the radius r. So we have to find the electric field at a distance r from the charge. So this is the r, and we'll see that the electric field will be outwards, and the area vector is also outwards. If I draw a small element over here, so the electric field will be in this direction, and area vector will also be outward normal. Now from the Gauss law, we can say that flux is equal to the charge enclosed upon epsilon naught, and we also know that flux for the closed surface will be E dot dA, right? So we can solve this integral, and we'll see that we'll get the electric field which we know for the point charge. Okay, so if we solve it, the integral, we have uniform electric field, so we can take it out of the integration. Now the integration will be of dA, and that is equal to charge enclosed upon epsilon naught, right? So we know the surface area for the Gaussian surface, that is 4 pi r square. R will be small, we have taken the radius E into 4 pi r square, right? And that is equal to charge upon epsilon naught. Now if we take it to that side, we'll get 4 pi epsilon naught r square. So now the second application is we have to find the electric field due to long charged wire with the help of Gauss law. So whenever I write the long will mean that the wire is infinitely long. Okay, otherwise the finite length will be given to you. So let me draw a wire, and it has a positive charge on its surface. Okay, so it is infinitely long. Now for the point charge, we have drawn the spherical Gaussian surface. While for this case, we'll draw as I have told you, for the wire we'll draw the cylindrical Gaussian surface. So I'll draw a small cylindrical Gaussian surface over the wire. Let it be of this shape. So the electric field due to the wire will be radially outward in both the directions. Let me draw it like this. Okay, now for the Gaussian surface we have a surface A, and let it be surface B, and let it be C. So if I draw a small element over the surface A, so the electric field will be in this direction, while the area vector will be outward normal, that is in this direction. Now if I need to find the flux through the A surface, so I'll write it as E dot dA, right? Now EDA, so the angle between the two is 90 degree, so it will be cos 90, which will be equal to 0 degree, and this will be the same for flux due to surface B. If I draw the area elements here, small element, and the electric field will be in this direction, while the area vector direction will be outward normal. Again the angle between the two will be 90 degree, right? So the flux for the two will be 0. Now we have to calculate the flux for the curved surface C. So this is the curved surface, so the flux will be E dot dA. Again we'll write this formula, and it will be electric field will be we can take it out of the integration since it is uniform in nature, so it will be EdA, right? Now the let me take the length of the cylinder will be L. Okay, so the flux will be E into area will be 2 pi RL, where R is the radius of the cylinder. Okay, so this is the flux of the curved surface. Now we also know that from the Gauss law, that this flux is equal to charge enclosed by epsilon naught. Okay, and it is also equal to the closed surface integral of electric field dot dA. Now if I open the integral, so I have one integral due to the A surface, that is E dot dA, and the second will be due to B surface, again E dot dA, and it will be also due to C surface, so it is E dot dA. This is whole equal to charge enclosed upon epsilon naught. This is the Gauss law, right? So the flux we have seen that it is 0, and this term is also 0, so this term is equal to electric field into 2 pi RL. And since we were given that it is the wire which has the charge and it has the charge density lambda, so lambda is for the linear charge density, so it is the linear charge density. I'll substitute charge is equal to lambda into L upon epsilon naught, so L will be cancelled out, so the electric field will be lambda upon 2 pi epsilon naught R. So we can see that the electric field is inversely related to the distance, and if we need to draw the graph between the two, we can say that electric field is and here R, so the graph will be of something of this nature, right? So this is our second application of Gauss law. Now let's see the third application. Third one is we have to calculate the electric field due to infinitely charged sheet. Now we have a sheet, so let me draw a sheet over here. Let it be a plain sheet, and it has a positive charge on its surface, right? Therefore it will have the surface charge density sigma. Now from the symmetry we can say that electric field is normal to the surface of the sheet, right, in both the directions. So the electric field is this. Now for the sheet also we'll draw cylindrical Gaussian sphere. So let me draw a cylindrical Gaussian sphere over here. Now again we'll have its three surfaces. So the surface, this one is A, and this one surface B, and let it be C surface, right? Again we'll follow the same pattern, that for the surface A, if I have to see the electric field direction is this, and the area will be again outward normal, so this will be the dA, and similarly for this. So the pattern will be same, but there will be slight variation. So for the flux due to surface A is equal to flux due to surface B, and it is equal to E dot dA, right? And now the angle is not 90 degrees, they both are in the same direction, so we can calculate it to be E dA, and we can keep it like this. Okay, now for the second surface, that is surface C. So for the middle surface we'll write it as E dot dA. Now the electric field is in this direction for this curved surface, while the area vector will be in the upward direction. So the angle between the two is now 90 degrees, so it will be 0. Again we'll apply the Gauss law. So Gauss law, which states that for this integral, flux is this equal to this equals to charge enclosed over epsilon naught. So we are proving that for the all the three surfaces, flux A, flux B, and flux C is equal to charge enclosed upon epsilon naught, and for both A and B we have got it to be EA plus EA plus 0, which is equal to sigma into A, as we know that it is the surface charge. So for the surface charge density we know charge upon area, surface charge density is this. Okay, so we can write it to be 2EA is equal to sigma A upon epsilon naught. Now this cancels and we get the electric field expression to be sigma upon 2 epsilon naught. So this is our result, which is independent of the distance. Suppose if someone asks that electric field, you have to draw the graph for the electric field and distance for the planar sheet. So we'll see that it is not varying, so we'll draw in this way. So it is a constant graph since it is not varying. Okay, so electric field graph will be this way. Similarly, we can apply Gauss law for to find the electric field due to hollow charged spherical shell. Okay, so this is our last application. Now suppose if I have a hollow sphere. Okay, so this is my sphere which is hollow in nature, so the whole of the charge will be distributed on the surface of the sphere, right? Now we have to find the electric field due to this sphere. So let me draw a Gaussian surface. So the Gaussian surface will be spherical in nature and the electric field will be radially outwards for the string. Now let's first find electric field inside the shell. So for the inside the shell, we'll draw Gaussian surface inside. So inside it will be of radius small r. Okay. And the hollow charged spherical shell has the radius capital R. So now let's apply Gauss law. We can write the equation for the Gauss law is equal to charge upon epsilon naught. Now in the Gaussian sphere, let it call it to be A sphere. Okay, so the Gaussian sphere A has no charge enclosed within it. We cannot see any charge. Whole of the charge is outside the sphere. Okay, so sphere A. So there is no charge, so the charge enclosed will be 0 over here. So if the charge enclosed is 0, we can say that electric field, which can be written as this, so the electric field will also be 0, right? Now for the outside the shell, let me draw another Gaussian sphere which is outside the shell. Now it has, again let's consider its radius to be r, and let it be sphere B, right? So for the outside, we can say that, again if we write Gauss law, which is equal to charge enclosed. Now we can say that the sphere B encloses all of the positive Q charge. Okay, so now the charge is whole inside the sphere B. Okay, now you understand the difference of the charges and the Gaussian spheres. Now let's substitute this value. Let the whole charge on the spherical shell will be Q. Okay, so it will be E dot dA is equal to Q upon epsilon naught. Now the area for this Gaussian shell is E into 4 pi r square is charge upon epsilon naught. So the electric field comes out to be charge upon 4 pi epsilon naught r square. So this will be the electric field outside the hollow shell, which will act like a point charge since the expression is same. Now if I have to draw the graph for this, so the graph will be electric versus r. If I have to draw, this is r and this is the electric field, so let it be r equal to r, and we have seen that for the inside there was no electric field, so it will be 0 over here, while for the outside electric field variation was in this way. E is inversely proportional to r square. And if I need to talk on the surface for r equal to capital R, so it will be kq by r square. We just need to keep the value of small r equal to r on the surface and we'll get our result. Okay, so these are some applications of Gauss law, and in this lecture we'll study till here. Till then, keep learning. All